The second polytropic process is the constant volume process. A non-flow isometric process can be visualized with a rigid vessel containing an ideal gas. Now let's start our analysis by assuming that we are going to transfer heat into the gas inside the vessel. Since the gas cannot expand due to the volume restriction offered by the container, the only manifestation that a heat transfer process occurred, aside from the increase in temperature, is an increase in pressure. In the PV diagram, the constant volume heat addition process can be represented by a directed vertical line starting from the bottom at point 1 and ending at point 2 at the top. On the other hand, in the TS diagram, the constant volume heat addition process can be represented by a directed curve starting from the lower left at point 1 and ending at point 2 at the upper right. Again, the directions of the PV and TS diagrams are just the same. When one of the diagrams goes up, the other one shall also go up. Conversely, if we have a constant volume heat rejection process, we will still arrive with the same shape of the two diagrams, but the positions of point 1 and point 2 will just be reversed. Just like in the isobaric process, the relationship of pressure, volume, and temperature can be expressed using the equation of state of ideal gas, or using its alternative form. The only thing with the latter form is that since we know that the volumes of the initial and final states are just equal, we can simply cancel out v sub 1 and v sub 2 on both sides of the equation. Therefore, by separating all of the pressure factors on the left side and all of the temperature factors on the right side of the equation, we will arrive at the third form of expressing the PVT relationship during an isometric process. Now we go to non-flow work. Since we know that there is no change in volume in an isometric process, then the differential of the volume dV inside the integral will just be equal to 0. This is the reason why the non-flow work of an isometric process is just equal to 0. For the heat transfer during this process, it may be computed using the non-flow energy equation. But since we know that the non-flow work is just equal to 0, then this equation will just reduce to Q equals the change in internal energy. An approximate computation for the heat transfer is using the average specific heat at constant volume of the gas. But its exact computation involves using the property table of the gas and finding the values of the initial and final specific internal energies with respect to the initial and final temperatures of the gas. Now, how we compute the change in internal energy and the change in enthalpy is just like how we compute this under the constant pressure process. If we want an approximate solution, we simply use the average specific heat of the gas evaluated at 300 Kelvin. On the other hand, if we want the exact solution, then we consult the property table of the gas for the values of the specific internal energies or the specific enthalpies of the gas with respect to their temperatures. Now, the change in specific entropy can be approximated using the average specific heat at constant volume of the gas. Take note that if the final and initial temperatures of the gas are unknown, we can still find the approximate value of the change in specific entropy by using the ratio of the final and initial absolute pressures instead. The exact solution for the specific entropy is similar to the exact solution in the isobaric process. The difference is we now have a third term since pressure does not remain constant in the isometric process. If we are not given the values of the initial and final pressures, we can replace the ratio inside the natural logarithm by the ratio of the final and initial absolute temperatures.